move forward to the next speaker, which would be Artem Yakovliev. He actually also will be partially collaborating on constructing a new Light for Ukraine beamline at Solaris, and he would tell us about X-ray preparatory experiments before you going actually to the beamline at Synchrotron.
Yeah, hello. Can you hear me well?
Yes, yes.
So I will take, figuratively speaking, a step back and talk about what kind of experiments can you do before you go to the facility, to the synchrotron or XFEL. So luckily for me, I had the introduction already given by Katarzyna and Alexei. So I will just briefly mention here what is XAS and XS spectroscopy, and I will be mostly talking about them. So in XAS, we measure the spectra transmitted through the sample, and it is usually divided in so-called XANDES and XAFS parts, X-ray absorption near-edge spectroscopy and fine structure spectroscopy. And in the emission spectroscopy, we are measuring the spectrum of the X-rays emitted from the sample after excitation. We get the lines. Here are shown K alpha and K beta, and usually K beta lines are the most interesting for us from the chemical point of view. And from both XAS and XS, we can get information about our atom of interest, about its chemical surroundings, and other types of information. And usually when we are talking about the X-ray spectroscopy, we are talking about some kind of facility, either synchrotron or new X-ray free electron lasers facility. And why is that? Mostly because of the brilliance of such sources. Unfortunately, in the laboratory, Unfortunately, the laboratory sources just doesn't provide us with so high flux, so we cannot get a good quality spectra in lab, and we have to apply for a beam time and go measure this spectra at the facility. And also, unfortunately, this process can be quite tedious, and usually it takes around half a year before, in between, you submit your proposal to the facility and when your actual beamline starts. And other drawbacks would be, of course, limited flexibility, and usually you have a short allocated time, few days up to a week. And it means that you often have to work night shifts in order to get as much data as possible from your beam time. And of course, I would encourage you to apply for the facilities and go there and measure your samples, because there you can get the best possible spectra. And some type of experiments you just cannot do in the lab. They are only possible on the synchrotron or at XFEL. But at the same time, while you wait this time before your beam time, can you measure XAS success spectra in lab? And the answer is yes, you can. And for this, there are two main geometries which you can utilize in your lab. The first one is called Johansson geometry. Both of the geometries have three main parts. It's the source of the X-ray radiation. It's the dispersing element, in this case, spherically bent crystal, and the detector. And in Johansson geometry, unfortunately, you can get quite high resolution, but you have to scan the sample, and you have to scan the spectrum, and you have to scan it in quite a complex geometry. So both your crystal and your detector have to move in so-called Roland circle, and it involves several positioning stages which move in quite a complex way, as you can see. And I forgot to mention that crystal just disperses the incoming X-rays and select the one energy of the interest which you need, and then by scanning you can basically scan the spectrum. And the second type of setups which you can use in your lab is von Hammer's geometry. So here we have similar situations. We have the X-rays in, they pass through your sample, for example, of XAS, they pass through your sample. And you have also spherically bent crystal, but you have the 2D detector. And your crystal works in such a way that in one direction, in this direction, you get a dispersion. So you have different energies fall on different part of the detector. And in the vertical direction here, you get the focusing. So you focus all your X-rays on the detector, thus increasing the number of counts which you get. And for the X-ray emission spectroscopy, you have a similar situation. You just rotate this setup and you collect emitted light from your sample. And in this case, you have usually faster acquisition time. This setup is relatively simple to make, but it has a lower resolution than Johansson geometry. And in our lab, we have the second type of spectrometer. We have double von Hammes geometry-based X-ray spectrometer. So on the left here, we have an X-ray tube with installed polycapillary optics, which focuses the beam on the sample. Sample is fixed on the 3-axis position in stage, so we can move the sample around and find the best spot for spectroscopy. And then we have a XAS part. So transmitted light from through the sample, we disperse with the crystal and detect with this detector. And then we have the second part, excess part. So emitted light from the sample, we disperse with excess crystals and detect on the excess detector. And the big advantage of having this double spectrometer system is that we can do XAS and XS at the same time. So we don't lose time by doing one and then doing the second one and rearranging the setup around. And here are some examples of what type of spectra we can get in our lab. These are the spectra for 3D metal foils, so from titanium to zinc. So as you can see, blue dots are the data from our setup, and the red line is the data from the reference data from the synchrotron. And as you can see, we have quite a good quality spectra in the range from 7 to 8 keV. We can get this kind of data in 1 hour exposure time, and they are in a good agreement. And the discrepancies that you can see, for example, for lower energy and for higher energy are caused mostly by the fact that we are working in air. So the lower energy just get absorbed by the air, and also the efficiency of our detectors are the best in this range, 7 to 8 keV, and below and above, we are losing basically counts, so we're not detecting the incoming X-rays. And here are some examples of the samples. So here you can see the copper complexes. The one is a chemotherapeutic agent, and the second one is photosensitizer used in photodynamic therapy. And here are the spectra measured in our lab. So you can already see that this spectra can be used for some kind of preliminary analysis of the samples. And next, we compared this spectra to the ones gathered at the SuperXAS beamline and at SLS. And you can see that they overlap, and it means that basically we can use our laboratory data as a preliminary step towards the synchrotron experiments. Second example is more challenging. So we had a copper nanoparticles we wanted to measure copper nanoparticles in water solution. So first we did we captured XAS spectra of copper foil as reference and copper oxide pellets. But already with with our sample of nanoparticles in water, you can see the challenges that we have not enough counts, but still this kind of data is of great use for us because we can check our sample, the quality of it, and we can test different, for example, delivery systems. So these same nanoparticles were then brought to P65 at Petra and Polix at Solaris, and we studied in real time the oxidation of these nanoparticles by XAS spectroscopy. And this flow cell setup was first tested in our lab, and then we brought it to the synchrotron facility, and we saved time by not testing it at there, so we can get some preliminary data in lab. And the last sample I will show of spectroscopy is zinc selenide quantum dots. So again, on the right here, the gray lines you can see are the laboratory data, and the colored lines are the data captured, measured at Astra beamline at Solaris. And you can again see the good accordance of laboratory data to the synchrotron data. And you can even, in some good cases, you can even start predicting your doing a chemical analysis of your sample, even with laboratory data. However, if you want good quality spectra and good quality analysis, of course, you would have to go to synchrotron facility and get better spectra. And finally, I will take a little bit about the X-ray imaging, because we also do it in our lab here. So we are collaborating with Yakovliev University, and we are studying these samples of heart valve squeeze calcification. So basically, this age you can get calcification on your on your heart valve, and which will eventually lead to the serious heart conditions. And they take these samples, they put them into the paraffin blocks, and then here in lab we can do micro computed tomography imaging of these so-called leaflets, which are inside here, inside the valve. And later these paraffin blocks are cut on the microtome into the thin slices, and we recently upgraded our setup, so we installed the SDD detector. And because we already have 3-axis positioning stage, we can also, on the same setup, we can do XRF imaging. Of course, with not so good resolution. But this is another example of the experiments which you can do in your lab. And then if you want, for example, higher resolution, higher sensitivity, or you want to do, for example, experiments in time with good speed, then you can do them at the synchrotron facility. And in conclusion, I hope I could persuade you that you can get good XAS and XS spectra in your lab for suitable samples. Of course, a big advantage of such approach is that you have practically unrestricted access. You have to only fight with your colleagues for access to the setup. And you are flexible to modify your setup and experimental conditions as you need, which is not all. Sometimes it is available at synchrotron facility, but not always. And before the beam time, you can first get preliminary spectra of your samples. You can check the sample quality. Then by looking at the spectra, you can select the most suitable sample, which you would like to measure at the beam time. And to some extent, of course, the brilliance difference is many orders of magnitude, but you can check the sample stability. But it all comes with a price, of course. So first of all, you have a much lower resolution compared to the spectra measured at this facility. Sometimes you need a long acquisition times. For example, for some liquid samples, it would take up to a day to get a good spectrum from the sample. And quality of this spectra is not always perfect. And you would require, of course, for the same reason, you would require the higher sample concentration. And the last one is radiation safety, because you need to put your setup inside the hedge or some kind of shielding, and your staff have to go through radiation safety training in order to work with X-rays in lab. Of course, when you go to facility, you also have to go through training, but you need to have it constantly here in lab. And at last, I would like to thank all my group, my department of applied spectroscopy. Our also collaborators from Yakovliev University Medical College and from Solaris Synchrotron Radiation Center. And of course, staff at Beamlines, Polix, at Astra, at Solaris, because they were very helpful and supportive during our beam time at the facility. And all this work which I showed was funded by the National Science Center under multiple grants. So thank you for your attention, and all questions welcome.
Thank you very much. Is there any questions from the public? So I probably may have a question, very technical one. So I saw your basically X-ray emission spectroscopy setup. And the main question, so basically you have different set of crystals or you have only one for this energy?
Because Yeah, I got a question. So because we have to change geometry all the time, and for example, for all these elements, I believe it would not be possible to measure them with one crystal. So we have a set of crystals, and every time we change a crystal and we move the detector and crystal around to fit the geometry to for the specific energy. And we do it both for the X-ray absorption and X-ray emission. So this is, of course, is a drawback that you have to change the setup every time you change a sample.
Okay, perfect. Thanks a lot.